So the next section about statistics is really looking at how we can mathematically work with numbers to create some good information. All of us are really bombarded on a daily basis by statistics. There's statistics all around us. And so it's important for us to be able to be good consumers of that and really understand what it is that they're trying to tell us and how we can make sense of it. So this particular section on how to make sense of it really involves two pieces. One is measures of central tendency, so mean, mode, median, which I kind of think most of you are pretty familiar with. And then another type of statistical measure, which is measures of variability. So central tendency is how does everything congregate to the middle? But measures of variability is how do things spread apart? We have just a simple calculation of range that we can use there, but the one that we're going to also look at is standard deviation. Standard deviation, I think, for a lot of people just seems overwhelming, but it's very simply looking at how we can take this idea of centrality and how we have our mean value and then how our data actually spreads out around that. So if we were to define standard deviation, it's really the average that each of our values will differ from this mean. And there's a couple of things that helps us with. It will help us if we can see really, is our data really just sort of congregated to one side or the other side, or is it nicely spread out? So within this, we're going to look at how do we calculate standard deviation, but we're also going to look at the normal curve and how standard deviation really determines how we create that standard curve, and then how that visual of our data will help us to interpret the information that we have. So we will talk more specifically about how to calculate it and also how to interpret it. Now I want to explain the process of standard deviation. Standard deviation is looking at how our data spreads. And so there's a very specific process that we use. I would say that when we look at the formula for standard deviation, it looks a little bit daunting, but the reality is we know how to do all the pieces. So it's probably a little more tedious than it is difficult, if that makes any sense to you. So when we are calculating our standard deviation, we're looking at how each of our values differs from the mean value, okay? And the process we follow is that obviously first we will have to have had the mean, calculated the mean. We then take each value, subtract the mean from it, we square that difference, and then what we're going to ultimately do is add all those differences, okay? So the first thing we would have to do is we have to make sure we know what our mean value is. And in this particular case, it's 79.5. So I'm just going over the example here, at least a portion of the example that you'll find by standard deviation in your packet. So we had values of 49, of 68, of 75, of 76, all the way up to 95. So what we would do with that is I'm going to take my 49, subtract 79.5. That gives me a difference there of a negative 30.5. We square that, essentially we square that to get rid of the negative, to be honest with you. So we square that, and this value is 930.25. We do the same thing with 68. So we're going to get the 68 minus this mean. That difference is negative 11.5. We'll square it, and we get 132.5. So see how we'll do that? We do that for 75, we do that for 76, so on down the way. So ultimately what we do on this particular example, if we add all of the differences that we have, when we added all of those, you can just trust me on this, our our sum was 1,654.75. That was the sum of all of our differences squared. We're going to take that value, 1,654.75, and we're now going to divide that by 11. The reason we're dividing it by 11 is because there were 11 numbers that we were looking at. So this 11 is however many values we're trying to determine standard deviation for. So we take 1,654.75, we divide that by 11. When we do that, we get 150.43. Notice in this step we squared each of these values. So in order to actually undo the square, we're going to square root this. So that's the next step. We square root 150.43. The square root of 150.43 happens to be 12.26. Okay? So that's how we determine our standard deviation. Now what I want to do is I want to explain how that's even helpful or what we can learn from that. So that's what I'm going to do in this next piece. So now I want to explain to you the normal curve, because this is really how we use standard deviation to help us understand the data that we have. This normal curve is this nice symmetrical bell curve. I think sometimes you hear it referred to as a bell curve. What the bell curve shows us is that if we have data that's nice and evenly distributed, then it falls out in, again, a real specific pattern. The way this works is that our mean is our central value. We're going to use that. And then for our data, what we're going to do is we're going to add one standard deviation to this mean. We're going to add another standard deviation to this mean, and we're going to add a third standard deviation to this mean. When we're going to see how our data comes to the left, or kind of looks like what it looks like below the mean, we're subtracting a standard deviation each time. Now, what happens is if we have this natural, evenly distributed bell curve, that it distributes itself in a very specific way. Within one standard deviation, positive or negative, if we have this normal curve, 34% on each side of our mean exists. So in other words, it's kind of saying that with our data, 68% is within one standard deviation negative and one standard deviation positive. We go out another standard deviation, and this time we have 13.5%, 13.5%. So that now if we add these up, we have like 97% of all our data is between one standard deviation positive or negative. We go out one more standard deviation, and in the example that I have in the packet, we talk about another 2.35% on each side. There are some sources that are going to say 2.5 and 2.5 here. It's kind of irrelevant. The 2.35 allows for us to look at some data that might be sort of what we consider an outlier. So you're either going to see this as 2.35 or 2.5. Okay. So what it's really saying is that when we look at our data, if it truly forms a normal curve, these percentages are going to be what our data shows us. Okay? So the example that we looked at, we said our mean was 79.5, right? What I'm going to do, just for simplicity, is I'm going to call that 80. We also said our standard deviation was 12.29, and I'm going to round that up just to 12, or round it down to 12. Okay. So for the data we've been looking at, let's see how it looks on this distribution, okay? So when I create this, now my mean is 80. If I add a standard deviation, I'm adding 12. So this is 92. If I add another standard deviation, this is 104. And I add another standard deviation, this is 116. So for my value, this is kind of our values, this is kind of what we're looking at. Now I come over here and I subtract a standard deviation. So this one now is going to be 68 because I'm subtracting 12. If I subtract another 12, this is going to be 56. And I subtract another 12, that's going to be 44. Okay? So what I know is that with our data, this is how we spread out, okay? Now I'm going to look at this, and I'm going to place the actual values from our sample of data that we determined this standard deviation from. And I'm going to place it on here, and then we're going to look at it and decide whether or not it seems like it's this normal flow. Okay, that's what we're going to do. So as I look at this, we had a 49. Well, 49 is going to be in this section right here. So we had a score of 49. We also had a score of 68. So I'm going to come here. Just for sake, obviously this is right on the line, but I'm going to just put my 68 right there. We had a 75, a 76, still between here, right? 75, 76. We had a 79 still in here. Do you see where I'm getting these values? Is that these are the test scores we just used. These are the intervals that we set up. We go to 83, and there's actually two 83s, so that's in this category between 80 and 92. We have two 86s. And then we had a 94 and a 95. So here's our example. These are the 11 test scores that we use to determine the standard deviation, this mean and the standard deviation. So the question I might ask is, do my values form a nice bell curve? That's the question we're going to ask. To be honest, when I look at this, we certainly approach a bell curve, but the reality is that in order for it to be perfectly symmetrical, we have to have the same number here as here. Now that works because there's 4 here and there's 4 here. But 13.5% would have been here and here. Notice I have 2 values here. I have no values here. And on my last one, we have one value of 49 here and one, well, we have nothing here, all right? So if I were to ask the question, did this form a normal curve? My response would probably be to say, not really. It's close, but it's not a perfectly normal curve. So what does that mean? It's not a big deal whether it is or isn't. It just tells something about our data. But if I look at this, again, this gives me a good visual of our data. If I look at this, if I'm the teacher of this class and I see these scores in terms of how they fit with each other, I would say I'd be pretty happy with how the test scores are, because quite frankly, most of them are, well, many of them are above the mean. More than half are above the mean, okay? This is the outlier, so I would need to decide, you know, was that a bad day? Is this somebody who just didn't have a chance to study on the test or whatever? But I can get this visual and see. Remember, this was titled Measures of Variability. So how did that data vary? And that's what my normal curve can show me. I have one other example that I want to show you that is kind of an application of this. So I will do that next. So here's my example. Javen and Kedron recently read that the mean number of bottles of water consumed by each American in 1 year is 425. And the standard deviation is 45. So we just found out that the mean was 425 and the standard deviation was 45. That's what they told us. This is a really important sentence. It says, assuming the data are normally distributed. So that statement has to be there to do what we're going to do next. Assuming the data are normally distributed, what percentages of Americans consume more than 380 bottles a year? So we're going to use that. They told us that this was a normal distribution. As soon as they said that to us, we know we can put in our percentages. 34, 34, 13.5, 13.5, 2.35, 2.35. And that's because of the statement, assuming these were normally distributed. Coming down here to how we set this up, they told us that the mean number of bottles that were consumed was 425, and that the standard deviation was 45. So if we take 425 and we add 45 to that, we're going to get 470. If we add another 45 to that, we're going to get 515. And we add another 45 to that, we're going to get 560. And then when we go this direction, we're going to subtract that 45. So when we subtract 45 from 425, we're going to get 380. Subtract another 45, we're going to get 335. Yep. And we subtract another 45, and we're going to get 290. Now, we were able to put these values in because we knew it was normally distributed. That was our mean. That was our standard deviation. The bottom line question was, what percentage of Americans consume more than 380 bottles a year? So what that tells me is it's all of these intervals right here. It's this because this is where the 380 was the breakoff. So it's going to be 34 plus 34 plus 13.5 plus 2.35. So what we can say then is that 83.35% of Americans would consume more than 380 bottles of water each year.